Thought I would just go ahead and do some review problems that are in the review section of your textbook. So these review problems start at the beginning of page 300, or excuse me, at the bottom of page 300. The ones I'll be doing are actually starting on page 301. So if we just look at a few of these, let's look at, this is number 8 on page 301. This one asks for the Laplace transform of t e to the minus 7t. There are two ways you can think about doing this particular problem. Notice that we've got e to a power times a function. Remember when we had the Laplace transform of e to the minus a t times f of t, that is equal to f of the Laplace transform of little f, but evaluated at s minus a. I apologize, there's no minus sign there. It's e to the at, f of t. Okay, so notice over here we could do the Laplace transform of t. Laplace transform of t is 1 over s squared. But instead of s squared here, we would have s plus 7 because we've got a negative 7 in our power. So that's one way to think of it, is we've got e to a power times a function. The other way to think about it is the other theorem we have is if we have t to a power times a function, we can do the Laplace transform by doing negative 1 to the n, the nth derivative of the Laplace transform of little f. So let's think about this problem in this fashion. I've got e to the minus 7t. The Laplace transform of e to the minus 7t would be 1 over s plus 7. And then t to the first power would say take the negative derivative of that to get the Laplace transform. And sure enough, if you do that, you'll get 1 over s plus 7 squared. So you can use either theorem in this case to evaluate this particular Laplace transform, and you should get the same answer either way, which makes sense. Otherwise, it would be a really, really bad theorem. Let's illustrate this idea of e to a power shifting something again. This is number 10, same page. It wants the Laplace transform of e to the minus 3t sine of 2t. Again, we want to use this theorem that we used in the first way we did the first problem. We're going to use that theorem that I just put a little box around in the upper right-hand corner. The Laplace transform for sine of 2t would be 2 over s squared plus 4. And then since we've got e to the minus 3t in here, we would have s plus 3 instead of s. Again, I'm going to give you the table that's in the back of the book on your test. So I'm going to expect you to be able to use the table to do these problems. So you don't want to be left out trying to memorize all these Laplace transforms for these different types of functions. One more as far as being able to do ones that are transformation things. If we look at number 12, same page, Laplace transform of sine of 2t, unit step function of t minus pi. All right, so remember your unit step function here, the theorem we want to use here is that you have Laplace transform of unit step function of t minus a, f of t minus a, that's e to the negative sa times the Laplace transform of just the f without the a in it. So the hardest part about these types of problems is trying to rewrite the function that's multiplied by the unit step function in terms of t minus a as the variable, not just t. So looking over here, we've got sine of 2t instead of sine of 2 times t minus pi, because t minus pi is what the argument is in here for the unit step function. Well, luckily for us, if we just replace the t with t minus pi, we don't change the function in this case, because really all we're doing, if I replace the t with t minus pi, in this particular case, notice that all we're really doing is subtracting 2 pi. Well, the period of the sine function is 2 pi, and we know that if we subtract 2 pi or add a 2 pi or any multiple of 2 pi, either add or subtract, it doesn't change the function. It's the idea of the period being 2 pi. So in this particular problem, putting a t minus pi in for t doesn't change the function at all. And now when we do our Laplace transform, the u to the t minus pi, or excuse me, u of t minus pi part becomes e to the negative s times pi, or pi times s, whichever way you want to write it, times the Laplace transform is just sine of 2t, which for us will be 2 over s squared plus 4. Notice there's no shift in the s here. The shift is taken care of by this e to the minus s pi piece. There's where your shift comes in. So those are kind of the big Laplace transforms for shifting things in this case. We should be able to work backwards as well. If we look at, say, something like number 15, same page, we want to do the inverse Laplace transform of 1 over s minus 5 cubed. Well, in this case, we notice that the basic form of this is 1 over s cubed. Now remember, the Laplace transform of t squared would be 2 factorial over s cubed. So to be able to do the inverse Laplace transform here, I notice that I need a t squared, but I'm going to adjust for this 2 that would be in the numerator. So we would have a 1/2 t squared. Now the s minus 5 piece is a translation piece, and the way we handle that, of course, again, is looking at it as e to the 5t. Because that 5t, or yeah, the 5t part here, that 5 is what this translation piece is here. Let's look at another one of these. Let's look at number 17. We want the inverse Laplace transform of s over s squared minus 10s plus 29. Now you may have to use a partial fractions in some of these, but unfortunately this particular quadratic in the denominator is not reducible. It's not factorable. You can check pretty quickly it's not factorable. So remember, instead what we have to do in the denominator is complete the square. To complete the square in the first part, I would need to have a plus 25. So really I need to borrow 25 off of this 29. So I would have s over s squared minus 10s plus 25 plus a 4. Or we would have s minus 5 squared plus 4 in here. All right, notice I've got this translation piece. The s has been replaced with s minus 5. I don't have the same thing up here. So I'm going to need to rewrite the top 2 and split this into 2 pieces. I need to write this as s minus 5 over s minus 5 squared plus 4, and then plus 5 over s minus 5 squared plus 4. The reason we do this, again, remember, we're trying to use this theorem that we had back at the top. I got to scroll all the way back up here. This theorem here says that if we've got a translation of s minus a, that means that there was an e to the at piece that we started with. We're working backward here to get our inverse Laplace transform. However, notice it says f of s minus a. This means wherever we would expect to see an s, we should see an s minus a first before we can do the inverse Laplace transform. So going back down here again, notice we only had an s on the top. So I need to make, then, since I have an s minus 5 in here, I need to see an s minus 5 up here before I can do the inverse Laplace transform. Remember, wherever we see an s, we're going to have to see that translation piece instead. All right, so we made the minus 5 and the plus 5 to keep things equal and split it. So now everywhere I expect to see an s, I have an s minus 5. Now we can do the inverse Laplace transform. This is a cosine, so this will be a cosine of 2t, the 2 coming from the square root of the 4. I need to multiply that by e to the 5t because of the translation piece. Plus, now here I've got a 4 in the denominator. For sine, I need a 2 in the numerator, so I'm going to have to adjust with a 5/2. We'll have a sine of 2t. And again, the 2 in the denominator is coming from the fact that we need a 2 in the numerator to do the inverse Laplace transform for sine. And then, again, we multiply this by e to the 5t. So this would be our inverse Laplace transform in this case. Let's do a couple more here. I want to do one with at least a a unit step function in it and see if we can also get one that might be periodic. So let's look at number 18. 18 asks for the inverse Laplace transform of e to the minus 5s over s. All right, since I've got this e to the minus 5s piece in here, we know that we're going to have the unit step function of t minus 5 in here. I'm sorry, this was s squared in the denominator in the problem. If we just had 1 over s squared, we would know that the inverse Laplace transform would be t. But remember again with the theorem that we talked about up here, right here. This theorem says that when you have the Laplace transform of the function and you've got the unit step function involved, I'm going to have to replace the t with t minus a, whatever this a value is. So instead of having t, we would have t minus 5 because that's what's inside our unit step function. So that's what we get when we do those inverse Laplace transforms. Pardon me. Let's see about if we can do a couple here that involve rewriting a function in terms of unit step functions and then do the Laplace transform of that particular function. So one of those would be like number 30. The graph they give you in number 30 looks like the following. It's flat until you get to pi. It's 0 at pi. Then you get a sine wave, and then it's flat again. So this function is y equals sine of x, where x is between pi and 3 pi. All right, so we want to do the Laplace transform of this function. The first thing we have to do is write this in terms of unit step functions. Well, notice the function is 0 until we get to pi. So our function until we get to pi is 0, so I must have the unit step function of t minus pi. And then it changes to, I wrote this as sine of x, let's change it to sine of t. The function is sine of t when we hit t minus pi. And it's sine of t all the way until we get to 3 pi. And then it changes to 0. So I would need to multiply that by minus sine of t to subtract off the sine of t that we had. So this would express the function in terms of unit step functions. Now we need to do the Laplace transform. But before we do the Laplace transform of this particular function, remember we have to have this in terms of the argument for the unit step function. So I need, instead of sine of t, I need a sine of t minus pi. The identity we want to use here is that sine of t minus pi is actually just the same thing as negative sine of t. So we can rewrite this function as unit step, the negative of the unit step function of t minus pi times sine of t minus pi. And then the same thing would work here. If we replace the pi with 3 pi, well, that's like replacing pi with a pi plus a 2, or excuse me, replacing the pi with 3 pi is the same thing as just adding a 2 pi, which doesn't change the function. So this ends up being plus unit step function of t minus 3 pi times sine of t minus 3 pi. So now we can do our Laplace transform. We get negative e to the negative pi s. The negative e to the negative pi s is coming from this. And then this will be times 1 over s squared plus 1, because that's the Laplace transform of just the sign. And then we get plus e to the negative 3 pi s times 1 over s squared plus 1. So once we get the function in terms of the unit step function, and get our arguments in terms of what the argument for the unit step function is, then doing the Laplace transform is just a straightforward application of the theorem we talked about before. All right, let's see if we can do one where we get something that's periodic I don't see one here in the chapter review. So let's say we had something like the following. Let's say we had something that was at 2 up until 2, and then it was 0 up until 4, and then it was 2 again up until 6, and then 0 up until 8, and so on down the line. This is going to be a periodic function because it's repeating every 4. So we notice that the period is 4 here. The theorem we're using in this case is if we have a periodic function, the Laplace transform of the periodic function will be 1 minus e to the minus s times the period, capital T is the period here, integral from 0 to the period of e to the minus st f of t dt. This is the theorem that we're using for periodic functions. So capital T here again is your period. You're going to actually have to compute the integral here, but this one won't be too bad since we've got just a constant times the function in this case. So for us, the Laplace transform will be 1 over 1 minus e to the negative 4s, again 4s because the period is 4, integral from 0 to 4 of e to the minus st f of t dt. Well, notice that from 2 to 4, the function's 0. So really, all we get here is 1 over 1 minus e to the negative 4s, integral from 0 to 2 of 2e to the minus st dt. Again, we don't need to worry about from 2 to 4 because from 2 to 4 the function is 0, and from 0 to 2 the function is 2. So that makes our life much simpler from an integration standpoint. This is going to be, remember we're integrating with respect to t, so this will be negative 2 over s e to the minus st, evaluated from 0 to 2. And again, we're plugging these numbers in for t. So we would get 1 over 1 minus e to the negative 4s times, we would have 2 over s minus 2 over s e to the negative 2s. So that would give us our Laplace transform for that function. We could simplify it a little bit, but at this point I just want the Laplace transform, so I don't need to worry about simplifying it for our purposes. All right, I want to do one more where we have to do the Laplace transform of an equation to solve, and it involves a convolution integral. So let's look at number 37. We've got y prime of t equals cosine of t plus the integral from 0 to t of y of tau cosine of t minus tau d tau. And the initial condition is y of 0 equals 1. Here's that convolution integral idea. Notice that the convolution, you have function of tau, second function of t minus tau. When we have a convolution integral, remember that the Laplace transform for the convolution is just the product of the Laplace transforms for the two functions. So if we do the Laplace transform of both sides here, we get s f of s minus little f of 0 equals Laplace transform for cosine is s over s squared plus 1. And now we're going to hit this convolution integral. I don't know what y is, so its Laplace transform we're just going to write as s. Laplace transform for just cosine, I don't need to worry about this as t minus tau. It's just remember, if this is the convolution integral, I'm going to treat these functions like they're just functions of t and looking at their Laplace transform. So this will be f of s times s over s squared plus 1. All right, so now we're ready to do what we've done in the other problems. We collect our f of s's and do inverse Laplace transforms. This is 1, and I'm going to move it to the right-hand side, and I'm going to need to move this to the left-hand side and factor off the f of s. So when I do that, I get s minus s over s squared plus 1. This will equal 1 plus s over s squared plus 1. We'll divide to get f of s by itself. And now that expression on the right-hand side, we could simplify it. It wouldn't be that hard to simplify, actually. I just needed to multiply top and bottom by s squared plus 1. Maybe I'll actually do that just to be able to type this into GeoGebra a little bit nicer. If I multiply the top and bottom of this big fraction by s squared plus 1 and then distribute it to the top and the bottom, that's what we would get. And that's a little bit easier to type into GeoGebra just to get our typing work to be a little bit more minimized. So let's go over here. We want to do inverse Laplace of the top was s squared plus s plus 1, and the denominator was s times s squared plus 1, and then minus s. Let me just double check and make sure that was really what I had. S squared plus s plus 1, s times s squared plus 1 minus s. That was what I said. Is that what I typed? That is what I typed. There's our inverse Laplace transform, which is good. So we can go back over here. So our f of t then was t squared plus 2t plus 2 all over 2. Let me just double check and make sure that was the right answer. Yeah, okay. So we really do get that for our final answer. So hopefully this review of doing some Laplace transforms in addition with the other videos that I've already shot will help you study for your test for tomorrow. So, all right, good luck on tomorrow. We'll see you then.